has some kind of peculiarity. We will talk about it. So we will actually take a look at these structures. First, we will try to see, we will basically try to solve these structures and all the intermediate steps. And I will try to put some more emphasis on the free body diagram part so that it is clear, right? It is so that any doubts, if you may have, you get them clarified now. Okay, so the first one we will start with, it's a truss. It's a very simple truss, right? All of you must have solved these kind of trusses a number of times. Let me assume that these angles are 45 degrees. Okay. And I have not solved this truss today, so sometimes I'm actually very prone to making mistakes while I'm doing it live. So please help me out. Please pay attention, and if I make a mistake, please let me know. Okay. All right. So first we will start with the determinacy calculation, right? So in the lecture notes I have shared with you, you can actually, whatever method you are used to using for trusses, you can continue to use that. I tend to use this method where I take b plus r minus 2j. It is an expression that just helps me out to do it quickly, this formula. Otherwise, you can just do it number of equations and number of unknowns directly. Okay. So each bar basically, at each joint here, if you look at each joint, you have two equations. Okay, so each joint provides you two equations. And how many unknowns you have? For each bar, you have one force. So that is one unknown, and each reaction is one unknown. So these are total number of reactions, total number of unknowns, rather, b plus r, and minus 2j represents the number of equations, because each joint gives you two equilibrium equations. This is a plane truss. Okay, so there will be one equilibrium equation in this direction, another one in this direction. So this will be the total indeterminacy value, okay. Static indeterminacy, that is. So I'm not talking about kinematic indeterminacy yet. Kinematic indeterminacy becomes important when we talk about stiffness method. Okay, so in this case, b plus b is 3. Reactions are also 3. How do we know? One reaction here, one reaction here, one reaction here. Total 3 reactions, 3 bars. So b plus r minus 2j. How many joints? 3 joints. So 2 times 3, that gives me 0. So this is a determinate structure. Okay. Now, we should keep in mind that I have not discussed yet how to estimate the stability of a structure. So this is a determinate structure if it is established that this is a stable structure. Okay. We have not discussed how to figure out whether this is a stable structure or not. This is a stable structure, but we have not discussed it yet. So what you can say is determinate if stable. Okay. It may not be. Only if it is stable, then this is a determinate structure. Okay. This particular one is stable, but we may not know yet. Fine. So this is the first part that is done. Then the second part comes of calculating the member forces, right? So how do we go about doing that? So should we draw the free body diagram on the joints, or should we draw the free body diagram on the members? Okay. So let me first start with, which joint should I start with? Joint B seems like the one to start with, right? When we solve any truss, a plane truss particularly, how many equations when we are starting to solve and we use the method of joints, let's say there are 2 methods of solving a plane truss problem, right? Or a truss problem. Which are the 2 methods?
Method of sections, method of joints.
Correct. So method of joints, let's say we go with. So in case of a method of joints, which joint do you start from?
Join with the minimum unknowns.
Minimum unknowns, exactly. Right. So at C, for example, you have 2 member forces and 1 reaction. Right. So there are 3 unknowns. Correct. Joint C's own equilibrium equations can give you only 2 equations. Right. Balance force in x direction, balance force in y direction. Only 2 equations, but you have got 3 unknowns. So if you start with joint C, you cannot use the method of joints fully to solve it, because you will get 2 equations, but you will have 3 unknowns. You will not be able to solve. Then you have to bring in other equations. That will not be really a method of joints. You will have to solve these equations of equilibrium at C, equations of equilibrium at A, equations of equilibrium at B simultaneously in that case. Then that is not a method of joints. Method of joints is basically you write the equations of equilibrium at B and solve them. or at A and solve them, or at C and solve them without having to move to the next joint. And that can happen only if you have number of unknowns at that joint equal to the number of equations. So at B, what we see is that we have two unknowns. This is joint B. We have two unknowns. So we will start with joint B because you have got two unknowns and you have two equations at any given node or at any given joint. So we will start with joint B. Okay. So at a time you can solve only for the joint that has only two unknowns in a plane truss. Okay. In a space truss, you can solve for any joint which has how many unknowns? Three unknowns. Space truss, right? Space truss, you have got three equations: sigma fx 0, sigma fy 0, sigma fz 0. So that three equations means three unknowns can be solved. But right now I can solve only two unknowns. Okay. Now this is joint B here. So now I'll apply this force P on this joint. Can we draw the free body diagram of this joint? So this is the force acting. Okay. And then there must be some other forces acting on this joint to balance this. And these forces must be coming from the other members. So the free body diagram of this joint should not show this member, these members. So when I'm drawing the free body diagram of joint B, I should not show the member AB along with that or member BC along with that. I should only show the joint B. Okay. And the forces must be coming in this way to balance this P. Even if you don't know the direction already, you can assume it to be other way. Because if you don't know, you can say that force is coming this way. Let's say we don't know. Okay. Let me make this a little bit shorter so that I can accommodate all this. Okay. Now, how do I get the values of forces? Let me call it F, B, C, and this is F, A, B. Can you even read it? No, it must be getting very, very tiny. Okay. You can see forces FAB and FBC, right? How do I know that what their direction and what their values are? How would I calculate their direction and values?
Sigma fx and sigma fy.
Correct. Which law of Newton does that come from? Which law says that sigma fx should be 0? Ranjit, you want to say something?
Yes, sir. It's first law.
First law, very good. Yeah, so first law or the second law. So acceleration is 0. In the first law, it says that when the acceleration is 0, the sigma fx has to be 0. So this is coming from the first law. So from the first law, now I'm not going to solve it. Of course, I know all of you know already how to solve it. So I will save some effort. Okay. So my forces have to be, these two forces have to be in such a way that they balance, their vertical component balances P and horizontal components cancels out each other. So if the two forces are equal and they are acting at equal angles, that is 45-degree angle, horizontal component will automatically cancel each other out. The vertical component of each one of them has to be P by 2. Okay. So that means this force has to be P by 2 multiplied by root 2, right? If this is the force, that its the vertical component will be P by 2. Agreed? I'm not making a mistake here, right? And this you will get by just by doing sigma fx is equal to 0, sigma fy is equal to 0, which I can further simplify as P by root 2. Fine. So that is the free body diagram of joint B. Now, how about the free body diagram of member AB or member BC? Okay. So look at member AB, for example. I'm still drawing joint B just to keep things in, like, in close proximity so that you. Now this force we have found already. Okay, this force we have already calculated. So now what will be the force at this end? Will it be this one or will it be this one? How much will it be?
P by root 2.
Okay, so this is one option, this is another option. Which option is correct, 1 or 2? Whether it is 1 or is it 2? Which one is?
1, sir.
2, sir.
2.
2, sir.
How many? 2. Most of you are saying 2. Yeah. So it is actually 2. And how do I know that? Those who are saying 2, can you please tell me which law of Newton tells you that this is the force? This is the force value and this is the direction of the force?
Third.
Third law.
Third law. Exactly. So let me get more space here. This is that member. This is that joint B. I'm just separating them so that I can draw all these forces. So on this joint, I had found out that this force is P by root 2. Okay. Now, where is this force coming onto joint B? When we draw the free body diagram of a particular object, so the object of my interest right now was this joint B. Okay. So when the force is coming onto joint B, we don't show where the force was coming from, but we have to account for it. Now, the Newton's third law tells us that for every action, there is a reaction. And that reaction is on the object that was applying the action. Okay. So this action of P by root 2 was acting on B, but it was being applied by the member AB on joint B. Okay. In this direction. So the reaction has to be equal opposite on member AB. And that will be P by root 2. That is Newton's third law. Okay, this is not coming from first law or second law. Now, when you solve this particular object again, so this is member AB, P by root 2 is acting here. If I don't have other balancing force, this member will fly away. So to keep it stable or in equilibrium, sorry, not stable, to keep in equilibrium, I have to have another force of P by root 2. Which law of Newton is telling me that this force P by root 2 has to be there? Which law?
First law.
First law. Now you see the difference between the first law's application and the third law's application? Correct? So if
Yes,
if it were a dynamic equation, if it was a dynamic problem, your first law would not be exactly giving you P by root 2, P by root 2. It will be giving something else because there is a inertia, that there is this acceleration part coming in. Okay, so the two forces will not be balancing. The two forces, net force will give you MA term. Correct? So first law will not exactly give you equal values here, but the third law will still give you exactly equal values, even in the dynamic problem. Got it? So that is something that you have to be mindful of. So likewise, you can keep going. So since now, going further down, this member, now when the forces on this member are acting like this, is this in compression or this is in tension?
Compression.
Compression, obviously, right? So this is compressive force on the member. Now, if you only show the forces on the joints, sometimes it is difficult to visualize whether the force is tension or compression on the member. So that's why always split joint from the member. So when you split the joint from the member, you separate them, then and you apply Newton's third law, then you can very clearly visualize whether the forces on the member are tension or compression. And when you do it enough number of times, you should be able to do it much faster than. So now for this joint, what will be the direction of the force? On the member, the direction of the force is this way, right? So on the joint, Newton's third law again, the member force will be, the force on this member will be this way, opposite and equal. This is one direction, this is exactly opposite direction of P by root 2. Fine. So now for this joint, again, I have to solve equilibrium. That is Newton's first law. I can have a reaction from this side. I can have a reaction from this side. This reaction has to be P by root 2 divided by root 2. That's vertical component of this one. So that is P by 2. This reaction has to be P by root 2 divided by root 2. Again, P by 2, but in the opposite direction. Right? So my arrow will be in this direction. That is P by 2. Okay. This member again, This member is member number AC. Now on this member, since this joint is being pulled in this direction of by P by 2, this member must be pulled by the joint in the opposite direction by P by 2. Salman, you are following it?
Yes, sir. Yes, sir.
Okay. Yeah. So this member is being pulled by P by 2. Now again, Newton's first law. So this P by 2 we got from the third law. Again, we will apply first law. Again, we will apply first law, which will give us a balancing force on the other side. It is coming from first law. Okay. Again, the node comes. Now for this node, we get a force of P by 2 here. And you can split a structure into as many parts as you want until you are confident that you have taken into account all possible reaction and all possible combinations of Newton's third law, action and reactions. Okay, there is no upper limit to how many times you need to divide it. And this one could have a vertical reaction, and this one could have a force in this direction, right? So now I know that the horizontal force here is P by 2 on this joint. Sigma Fx has to be 0. That means this force has to be, the horizontal component of this diagonal force has to be P by 2 in this direction. That means this force has to be P by root 2. Okay, so its horizontal component will be P by 2. Horizontal component will be P by 2 in the rightward direction. Okay, so P by root 2 here, so its vertical component will be automatically balancing it. So this reaction will be P by 2 again. Okay, and now you put this member in place. You got P by 2 acting on this joint this way. That means the member must be the equal and opposite reaction again from the third law. So this one we got from the first law. Okay, this P by 2 we had got from the third law. Then this P by root 2 again, we will get P by root 2 here, which is again coming from the third law. Okay, and from the first law we will get P by root 2. Fine? All clear, right? Then this has to be balanced by P by root 2 here. That's what we had started with. Okay. And there was, of course, a P force active here. Is that clear? So that's how you split into member and the rod and the joints. And you can see that the whole thing is in equilibrium. Now you can cut anywhere in the middle also. Still, you can draw the free body diagram of that particular part. There is no change. Okay. So that's how you solve this system. So this is just the member forces we have calculated and reactions we have calculated. So what are the reactions we got? We got compressive force of, we got a compressive force of P by root 2 here, right? We got a compressive force of P by root 2 and tensile force of P by 2. Got tensile force of P by 2 and a compressive force of P by root 2. Okay. So when I'm marking these forces, these are compressive and tensile forces, and my sign convention is plus minus accordingly. Tension for positive, or positive for tension, negative for compression. And these forces, when I was showing the joint forces, those are just the external forces individually. These individual forces or these reactions. So these are P by 2 this way and P by 2 this way. Fine. A very simple system. I didn't pick a very complicated system to solve, just to elaborate. Any questions from this part?
Excuse me, sir.
Yeah. Tell me.
So after solving the truss, we show the arrows directly in the main truss, like we have taken in the question above.
You're talking
So
about first figure, or like which arrows?
the very
Reaction?
first diagram. So we show everything in one diagram only. So there we have to show with respect to the joints, arrows with respect to joints, or arrows with respect to the member.
That's
That's
your
the
call.
question.
That is your call. Whatever you want to show. If you just mentioned that you are showing the forces on the members or you are showing forces on the joints.
Okay.
See, for me, it is easier to show the forces on the members so that I can visualize and I can very clearly see that it is tension or compression. If you show the forces on the joints, then that translation of the direction of forces on the members you have to do in mind. Like mentally you have to do that inverse the force direction. You agree? So what I mean is
Yes, sir.
that, see, on joint B, for example, here you can see joint B that I'm circling right now. On joint B,
Yes, sir.
you have forces acting in this direction, right? P by 2 and P by root 2 you can see. But from here, if you can directly do the mental calculation and say that, okay, this corresponds to compressive force on the member AB, fine. But usually, if you are not that well trained, your brain is not trained that well, then it might be better to split it and show the forces on the member separately and say that, okay, yeah, this looks like a compression on the member. So once you draw these forces, this P by root 2 that I've shown here, once you draw it, then it will be very easy to visualize that, okay, this is compression on the member. Okay.
So,
I hope
sir,
I
we
answered.
are saying.
Yeah.
So, sir, we are actually saying that it is compression on the member, but we are showing it like a tension. I mean, suppose there is just a rod, and on the rod, how we show the tension. If we are showing like that in the truss, we are calling it as compression.
No, I didn't follow you. So you are saying this P by root 2, if you show, this is the one that you are saying, if you show only like this?
Actually, I am saying that in the assembled diagram, the very first diagram in the question which we have taken, if we were to
Yeah.
show all the arrows in that assembled diagram.
Why do you want to show the arrows? I mean, how would you know on which member you are showing, on which part you are showing? So if I, let's say, put an arrow like this, then from there it is very confusing because I don't know whether you are saying that this arrow is acting on this member here at this location here, or it is actually corresponding to the location on this joint or something. So it is unnecessarily confusing. Or for example, if I put a, sorry.
But that's what normally we do, sir. Means maybe in the books or while doing the calculations.
Yeah, so basically different books may follow different conventions. That doesn't matter. See, how you represent is your call. But if you show forces like this, it is very difficult. I mean, somebody shows forces like these. I don't know whether I should call it tension or compression because I don't know whether you are showing this force acting on the member or you are showing this force acting on the joint. Who is applying that force? So I would not recommend drawing arrows like these within the member. This is not the type of forces arrows you are suggesting, right? The one that I just drew.
Yes, sir. Yes, sir.
Yeah. I would not recommend drawing arrows like that. That is confusing unnecessarily.
Okay, sir. Okay, sir.
Yeah, you should clearly mark the members like that is for your own good, so that you don't confuse between whether a force is this force is corresponding to the joint force or it is corresponding to the, because the joint is applying force on the member and member is applying force to the joint, and the two forces are in opposite direction, right? So when you
Yes,
put an arrow like that, you are not clearly specifying whether you are talking about the force that member is applying on the joint or the force that the joint is applying on the member.
yes, sir.
Yeah. Okay. Moving forward on this frame, so we will solve this frame also quickly. We will try to solve at least. So you've got frame ABC. Okay. And we will try to see whether this is first, it's a determinate or an indeterminate structure. What you see here is this triangle here between A, B, and BC at joint C, B. I'm showing a triangle. With this triangle is not necessary. I could have just shown it as this kind of number also. But sometimes in tiny drawings, it becomes a bit confusing. whether this is a rigid connection between at joint B, it is a rigid or it's a hinge. So for that, just to overemphasize that rigidity, we put a triangle here sometimes. Okay, so this triangle basically, triangle that I have shaded, that triangle basically means that it's a rigid connection at B. That means it transfers the moment. Okay, there is no relative rotation. Got it? So if if member AB rotates at B, member BC will also rotate by the same amount at B. Fine. So we will first start with the calculation of determinacy. Or static determinacy. Fine. So the expression that I typically use is R minus 3n for space frame. This is space frame, right? This can take bending moments. It's a space frame. R is the number of unknowns and n are the number of components. So each component is going to give me 3 equations, right? And the truss problem, each component that was joint, each joint was giving me only 2 equations because joint had 0 dimensions. Okay, so it did not have a moment balance. All the forces were always acting towards the joint. So the moment balance equation was not available. But in this case, each part, wherever I split it, it is going to give me how many equations? 3 equations. Sigma fx 0, sigma fy 0, sigma mz 0. So that's why 3n, that is for each part, and r is the number of unknowns. So if I don't break this entire structure into any subsequent parts, I just remove the boundaries. Then for each boundary, how many reactions do I get? I get 2 reactions for this boundary, and I get 1 reaction for this boundary. The total reactions are 3. Okay, and how many parts do I have? I have a single part. So 3 times 1. That gives me 0. So static determinacy is 0. I can, if I'm not confident, I don't know what is happening here, and I want to just be sure, I can split it. So let me split it here. If I split it, then what is my R value? I got 2 here, I got 1 here. And how many R's unknowns did I get here? Unknown reactions, unknown forces. How many? When I split it, 3, right? So earlier we had 3 plus we got 3 more because we split it. So 3 unknowns we got. Which are those 3 unknowns? If I can draw them separately. I got some reactions between them. So if there is a force acting on this member, and there is a force acting on this member, and there is a force acting on this member at this joint, these are the 3 unknowns. The same unknowns will be acting in the opposite directions here. Okay, that is a given. So they are not additional unknowns. Okay, the same 3 forces. So this force is same as this force. This force is same as this force in the opposite direction. This force is same as this force or moment. Fine. So I don't have to count them twice. I'll count them only once each. So 3 plus 3, these are 3 unknowns, 3 here and 3 here at the boundaries, and minus how many parts have I got? I've got 2 parts now because I have split it. So 3 times 2, sorry. 3 times 3n, right? So that will give me again 0. So this is the determinate structure. If I had, let's say, a hinge here, if this problem was this, then I cannot take the first approach. So you remember I had taken one approach where I had not split it into 2 parts. I had assumed the entire structure to be 1. I cannot do that because at the hinge, it is different from the rest of the structure. At everywhere else, I have 3 unknowns and 3 equations. So every time I split anywhere else, I get 3 additional unknowns and I get 1 extra part. So I get 3 additional equations. But that doesn't happen at the hinge. So at every hinge, you have to cut. If you don't cut, you are making a mistake. So that first way of single part cannot be used, but I have to cut here still. So if I cut it again, so what do I get? R minus 3n again. So R is 2 here, 2 here, 1 here, and how many here at B? How many equations do I have? Equilibrium equations. Sorry, not the equations. How many unknowns do I have? I'm sorry. How many unknowns do I have at B?
Two, sir.
2.
Yeah, 2 only, because moment is 0. We already know that hinge is given. So 2 plus 1 plus 2, 5. Minus how many parts have I got? How many parts have I got?
2.
Two, sir.
Okay, so that gives me minus 1. So it is less than 0. That's why this is a definitely unstable structure. Okay, fine. And you can never cut it into too many parts. So whenever you have a doubt, you can always cut it further. So let's say this is again that old rigid structure, rigid joint. Okay, this is a rigid joint, and I cut here. I can cut it 3 places, let's say. Fine. Then if I cut it into 3 pieces, reactions will be 3 here, 3 reactions. Yeah, 3 unknown forces. 3, 3, 9 plus 3, 12. So R minus 3N will be 12 minus 3 times. How many parts have I got? 1, 2, 3, 4. 4 parts. Again, 0. So what does that mean? It is a determinate structure if stable. We have not established stability. Okay. Even if it is 0 or this number is positive, it may still be an unstable structure that we can discuss a little bit later. Fine. So now I know that it is stable, so we don't worry about stability right yet. We know that this is a stable structure, and then if it is a stable structure, then this is a determinate structure. Okay. Moving forward. Now, how to solve this system? So we'll have to start with drawing the free body diagram. So we will start with, let's say, the horizontal member. Now, horizontal member has got this force W acting over the length L, and let's assume that 2 lengths are L each. Fine. So this W is acting on this member. What kind of forces can you have? You can have a vertical reaction here, that is this support C. At B, you may have a vertical reaction too. Correct? That is the 3 unknown forces between B at location B. This is one unknown force. Then there may be another unknown force, and there may be a moment acting here. Fine. Okay. Now let me move this member slightly away from here. Now, for this member, that is member AB, I believe, for member AB, I have to again assume some forces, right? So there is no external force applied directly on member AB, right? Whatever forces are applied, they are coming from member BC only. This is BC. Now, what can we say about the forces at BC? From equilibrium, let's try to solve some of these forces. So from equilibrium, we can say that this horizontal force, we can call it Bx. Okay, horizontal force at joint B. How much will that be?
0, sir.
0, right? And which Newton's law are we using here to say that Bx is 0? Which Newton's law are we using?
First law.
First law. Okay, from the first law. Okay, so this is 0. Moment need not be 0, right? And of course, the By forces, so this you can call it Bm or Mb. What should I call it? Mb. And I can call it this one as By. Okay. So, and B is the joint. So by need not be 0. Likewise, cy need not be 0. Cy need not be 0. Okay. So I know that by plus cy is equal to wl. Okay. And then there is a possibility of m acting, mb acting. But mb I cannot. Let me write an equation. It will not help me solve it much, but let me write it anyway, because I've got only two equations. Vertical force balance is this one, by plus cy is equal to wl, and another equation could be the moment balance. So moment balance will give me cy multiplied by l minus, let's say this is the direction of m, so cy multiplied by l is acting in the counterclockwise direction. So cy multiplied by l is a moment or is a bending moment?
Moment.
It's a moment, right? So I have to look at the sign in counterclockwise and clockwise direction. So sign will be positive or negative based on whether it is a clockwise or a counterclockwise moment, right? Not the sagging versus hogging. So cy multiplied by l is a counterclockwise moment. I'm calling it positive. So mb, the way I have shown it, it's actually a sagging bending moment. If it were a moment, if it were a bending moment, mb would have been a sagging bending moment, right? But I will show it as a negative because it is a clockwise moment, and what I need here in this equation is a moment value, not the bending moment value. Okay, so as a moment here, so that's where you need to differentiate between a moment versus bending moment. Right now, but the way I'm using it is a moment because it's a moment acting on this member, external moment acting on this member. So mb, okay, and what else? Minus wl square by 2. Am I right? wl is the total force acting at l by 2 distance. That is equal to 0. So now what has happened is I had the three unknowns, b, by, cy, and mb, and I've got only two equations. So I cannot solve them entirely here. So we'll have to wait for a minute. We'll just park them. Okay, we'll move forward. Now coming back to member AB. From Newton's third law again. So this part was Newton's first law. Both equations we got from Newton's first law, but Newton's third law suggests that these three forces will also have their reactions. Bx anyway was 0, so I will not plot Bx here. But there will be By, and By will have this direction here. That is exactly opposite of this one. And then there will be Mb. So Mb was in which direction here? In the clockwise direction. So I will change an Mb here in the counterclockwise direction. Now this is counterclockwise, right? Fine. And what kind of forces are available at A? I can have a horizontal force. I'll call it Ax. But I can have a vertical force. I'll call it Ay. Can I have any other forces acting on this member in any way possible?
No, sir.
No, right? Because at both ends, these are the only forces that can be applied. Bx we have established is already 0. So since now again, once you get the external forces on member AB, again you have to write the equilibrium equations for member AB. Now horizontal force balance will suggest that Ax is equal to how much? 0, horizontal force balance. So there is no other horizontal force acting on the member. So Ax has to be 0. Ay has to be equal to By. They are already acting in opposite directions, the way I have taken them. Okay. So Ay and By have to balance each other out. How will Mb be balanced? Can we balance Mb?
Moment about B.
Which moments would you take? So if you take moment about B, Mb is the moment, but and no other force is offering any moment about B. Is it? So my Mb has to be 0. Fine. Makes sense, doesn't it? Okay. You're not, don't seem to be convinced. Do you guys have any issue with this? Or at least speak out, no? Now you can't see the screen. Okay, you can see it, right? I'm waiting for you. Somebody. You don't seem to agree that MB will be 0?
Then in the that there also MB should be 0 now.
Yes.
That CY into L minus MB.
Yeah, but when we wrote this equation, we did not know MB was 0. So we kept MB, but we will put that back.
Oh, okay.
Okay. But MB, at that time, MB was a possibility. If, let's say, there was any force acting on this member this way, then MB would not have been 0. So we did not know that at that time. But when we solved for member AB, then we realized that no, MB does not have to be non-zero. MB is actually 0. And that you agree, right? At least from the equilibrium equation of part AB, you can see that MB does not deserve to be there. If MB is there, the member will not be in balance ever or in equilibrium.
Yes, sir. Yes, sir.
So, or otherwise, let's say we can write the equilibrium equation about B. So let's write the equilibrium equation about B. So MB is in a counterclockwise direction. MB plus BY multiplied by no distance, AY multiplied by no distance. They are all both passing through B. So no moment. And AX is also creating a counterclockwise moment. So plus AX times L is equal to 0. Now AX itself is 0. So MB is equal to 0. Fine. So now, after solving this part, I have got one unknown resolved. There are 3 unknowns: AY, BY, CY. 4 unknowns rather: AY, BY, CY, and MB. Now, MB is known, and AY and BY relationship is known. So now, putting this back into this equation, what happens? CYL is equal to WL square by 2. That means CY is equal to WL by 2. Okay. And BY will be equal to, CY is known here. BY will be equal to, again, WL by 2. Correct? WL minus WL by 2 will be WL by 2. And the same will be your AY, because here we saw AY was equal to BY. Fine. So if I can draw this frame again, I've got a reaction of WL by 2 here, reaction of WL by 2 here. Okay. CY, BY, AY, and BY is the internal force, which is not an external reaction, so I'm not showing it here. Okay. Cool.
Yes, sir.
Yeah. So if I want to draw the bending moment diagram, then I have to draw the internal forces also. So I take horizontal member, whatever it is, BC probably. It has got W acting here. It has got WL by 2 acting here. It has got WL by 2 acting here. What is the moment acting at this end? How much is the moment?
Zero.
That is 0. So basically, we got almost like a simply supported beam condition. So the bending moment diagram will be like this. Okay. How much will be this value?
WL square by 8.
You all remember that, right? WL square by 8 for a simply supported beam.
Yes.
What is the deflection of a simply supported beam under uniformly distributed load?
5 by 384.
384.
5 by 384 WL to the power
4.
4 by
Four.
100 to the power 4 by
EI.
EI. Okay, so now the vertical member, on the vertical member, you have got WL by 2 acting here, and you got WL by 2 acting here, nothing else. Okay, so this is fine. No bending moment. Okay, I could have also shown, instead of applying this vertical load W, instead of this vertical load W, I could have solved this system for a horizontal load acting this way. Okay. This is an interesting structure. It kind of intuitively, it gives you a feeling that this is an unstable structure because nothing is preventing it from falling over. This is a hinge, this is a roller. Joint A is a hinge, joint C is a roller, right? So it can very easily topple, but that won't happen because your joint B is a rigid joint. Okay. If I apply horizontal load, still it will be a stable structure. You can solve it. Fine. Done. Okay, I've got 5 more minutes. Should I extend the class or should I? Okay, let me see. We can do some discussions on stability maybe. So these are the equations that I was talking about: r minus 3n, r minus 6n, b plus r minus 2j, b plus r minus 3j, the equations that I have used today. Okay, these equations. All right, the short way of knowing whether a structure is stable or not is actually by calculating the determinate of the stiffness matrix. Okay, so that we will learn towards the end of this course. But right now, there are various tricks to calculate that or to find out whether the structure is stable. Some of those tricks are very powerful, but still they all leave some loophole. Okay, so none of them are surest way. So I'm not going to spend too much time on determination of stability. So I'm just showing you 2 examples here. The first example is a truss, right? So I have a truss like this. This is a truss, right? It looks like a truss. So if you do any of those calculations, b plus r minus 2j or whatever, and you look at this truss, the second problem, both of them, b plus r minus 2j will give you the exact same, or any formula that you want to use will give you exact same value of indeterminacy. But one of them is stable and one of them is unstable. Which one is unstable? Haripriya? Haripriya, do you want to answer? Between the 2 trusses, the one on the top and the bottom, which one is unstable? Are you around? Haripriya? Unmute your mic. Yeah. Which one seems like an unstable structure?
Second one.
Second one is unstable. How about the first one? That's stable. Why is the second one unstable? The second one, right? This is the one where the cursor is. Why do you think this is unstable?
If we
See, you
provide
gave an.
support,
Sorry. Go ahead. Go ahead, please.
in middle there is no support.
But there is no support in this one also in the middle. The top also, it is kind of, there is a hinge there too.
Yes, sir.
It is hanging. Did you see this hinge? This hinge is present in both cases.
Okay, sir.
Mohan Krishna?
Yeah, yes, sir. When we applied load in the first case, it tends to move downwards, sir.
Yeah. And the second one won't move down?
In the second one, it won't move, sir. There, it's formed like there is extra length is there, so that whenever we apply load,
See, it will move. No, your answer is correct. Now, I'm trying to make you use the correct words to explain what you are saying. So both of them will move. If you apply vertical load at the mid node, this is the mid joint, right? This joint is mid joint. If you apply vertical load, both of them will move. What is the difference between the movement of the first one versus the movement of the second one?
Yeah, in the movement of first one makes the structure unstable, sir.
Yeah.
It will be more when compared to the second one.
Yeah, the movement will be more, you are saying. In the words I would use is that the first one will start deforming without offering any resistance. So the stiffness at that time is 0. So any movement, as I mentioned before, any movement, even the smallest one, if that happens without offering any resistance, okay, then that is a clear sign of unstable structure. Okay, so you remember this one, right? So I had briefly mentioned this thing. There are unstable equilibrium, there is stable equilibrium, and there is. sorry, there is neutral equilibrium and there is stable equilibrium. In structural engineering, we call both of them as unstable. Even if it's neutral, I mean, we never have actually neutral. But let's say you have something neutral, then we still call it unstable. And this is the only one that is stable. It's known as stable. Okay. Now, if the system is in unstable equilibrium, what will happen is I'm just erasing it, something else. If I draw force versus deformation, so I am plotting deformation here and force here. And which force I'm talking about? I'm talking about a force that I apply here. And let's say it deforms by delta. Okay. So if it starts with a zero slope, then it is unstable in this immediate region. Okay. This structure, however, will behave like this. When I apply a force, it will not have a zero slope. It will have this kind of a slope. And as the force increases, it may become nonlinear. That's okay. As more and more force is applied, it will become nonlinear. But in the very beginning itself, it has a non-zero slope. Whereas in this case, it deforms without offering any resistance. In this case, it deforms, but as soon as it starts to deform, it starts to offer a resistance. Okay. So that's the very clear sign of stable versus unstable. Now, you are right. Now, just for the interest of the entire class, I would want to elaborate further a little bit on why am I saying that it will not offer any resistance. I'm sure most of you would know already. So if I apply any force F here, that is a vertical force, right? That vertical force needs to be balanced. So if I draw the free body diagram of this joint in the middle of this joint, it has got a force F acting here. But the two members that it is connected to, they are only in this direction, and they are bars, they are truss members. So they can apply forces in these directions. Okay. And no matter how much force they apply in these directions, they will never be able to balance a vertical force because their vertical components are always zero, no matter how large these values are, two horizontal values are. Their vertical component will always be zero. So the F, whatever I apply, will remain unbalanced. And that is why this is an unstable structure. Okay. But if I apply force like this, if I apply horizontal force at this joint, let me mark it exactly on the structure. If I apply horizontal force like this, you may never get to know that this is an unstable structure. Only when you apply this kind of a force, you will get to know that this is an unstable structure. But as long as we are calling it as a plane or plane truss, that means this movement is allowed. That means this is an unstable structure. Fine. But this one is not an unstable structure because if I apply force F here and draw the free body diagram of this joint, the two forces that are coming from the two members, which can apply forces like these, will have a vertical component. They are made of this vertical component. Both of them are made of this vertical component. Got it? So this vertical components will balance the externally applied force, and that's why this is a stable structure. Look at this frame, for example. I've got a nice frame here, which has got a lot of redundancy. So if you calculate the indeterminacy, it will turn out to be very, very high level of indeterminacy. If I can simply cut it all the way here, then I got three determinate structures. You got 3 plus 3 plus 3 plus 3 plus 3, got 5. So 5 3s are 15. You got indeterminacy of 30 in this structure. This structure has an indeterminacy of 30. Okay. If I just add one small member with a hinge here, so now this part is making this structure unstable. So this part, the I value that you can calculate in a similar way, will be very similar to 30. Okay. However, this structure will not be called an indeterminate structure. So this is an indeterminate structure. This one is and what kind of structure is it? The second one? What type of structure is it? Is it a determinate, indeterminate?
Indeterminate.
It's an unstable structure. How do we know that this is an unstable structure? If I take this member and apply any force here, it is connected with a hinge. So it will start going round and round without offering any resistance. Okay, it will move without offering any resistance. So therefore, this is an unstable structure. Okay. So the rest of the structure is same. I have just added one level of one small instability here. If you develop the K matrix for this stiffness matrix for this structure and you calculate the determinate, you will find that that turns out to be 0. Okay. Is that clear? You can start to distinguish between it is locally unstable, globally stable, this, that, but unstable is unstable. Unstable, I would stick with one definition. Okay, this is the sign convention. We have already discussed the sign convention for internal forces, right? So bending moment, shear force, axial forces. These are the sign conventions we are going to use. And you all know what shear force is and what bending moment is. So I'll not spend too much time here. Now this is the new chapter or new part of this discussion, which is on the calculation of deformations. So there are 3 different methods I'm discussing in this course for calculation of deformations of system. So which methods are you familiar with or most comfortable with for calculating deformations of determinate systems?
Moment area method.
Moment area method. Okay, that is one. Anybody else?
Conjugate beam methods.
Conjugate beam method. Fine. So you find conjugate beam method handier, huh? Easier to use. And for trusses, which method do you prefer? See, both these methods that you mentioned, conjugate beam method and moment area method, they by default have words moment or beam, right? So they cannot be applied to trusses. If you have a moment that is bending moment, right? Then it cannot be applicable to trusses. That is obvious, right? Or is it not? For trusses, which method do you use typically for deflection calculation?
Energy method, sir.
Yes, one of the energy methods you have to use. Correct. So I'll talk about. I'll not be able to. So there is Castigliano's theorem. There is virtual work method. I like the virtual work method very much. It's more universal and it is. I think it's pretty quick too. And I like the moment area method also for beams, wherever beams and frames are concerned. But it has. It is very quick for certain systems, but it can be very cumbersome for some other systems. It depends on the type of boundary conditions you have. Okay, so we will talk about that. The first one is the double integration method. This is basically the most basic standard method. Okay, I would suggest that you maybe in the next class, because I didn't go through the moment area method. This one I can solve in this course today itself. Do you want me to go through the double integration method? Just I think development of the bending moment diagram might be of interest. You might have forgotten a little bit of some parts of it. Okay. So the problem is given as this. And there is a load acting here, right? The first part is 2L long. And the second part is L long. And a force P is acting at the free end. And we can call it part 1, we can call it part 2, we can call it member A, B, C or something. That's okay. So we want to know the bending moment diagram of this problem. Why do we want to know the bending moment diagram? Because we are assuming that deflections are caused only from bending moments. Okay. Shear force is not causing any deformations, and axial forces are also not causing any deformation is a wrong way of saying it. It's basically that we are ignoring the other types of deformations. Okay. So we will start with the bending moment diagram. Now, bending moment diagram seems pretty, and all of you must have done enough exercise of this type of a problem. So let me first draw the free body diagram of part 2. Okay, I've got an external force P acting here. Fine. I have got one reaction coming in here. Let me separate it just to keep, because the member is continuing, right? So let me draw the free body diagram of two things together. Axial force we are ignoring because there are no axial external forces acting, so there could not be any axial forces. So I'm ignoring the axial force part. It's a beam problem, purely a beam problem. So if there may be a bending moment acting here, correct? Will there be a moment acting at this free end? It can, right? Because there is a continuity of the member. From there, the moment can come. That is an external moment for this part. But what will be the moment on the second part? A reaction. That is third law. That will be in the opposite direction. So this is in the clockwise direction. This one is in the clockwise direction. This will be anti-clockwise direction. Fine. Then what else is possible? You can have, let me draw this support separately. Fine. You can have some kind of a vertical force. So now that vertical force, there may be vertical force interacting between these two members also. And there can be vertical force interaction between these members also. Yeah, please.
So that should be in anti-clockwise now. That L member.
You want me to change it to anti-clockwise?
For the equilibrium, it should be in.
No, I'm just assuming any directions. I'll get to the other signs soon.
Oh,
I'm
okay,
not.
sir.
I've not written the first Newton's first law equations yet. Equilibrium equations yet.
Okay.
Let me take this sign. Okay, and at this support, I've got a reaction here, and maybe there is net reaction coming out from here. I'll put a small part in the middle. Okay. So this is a small tiny part of the beam which is zero length. I'm just showing it here just for clarity. I will have a vertical reaction coming to the support from here. This itself represents the support. So vertical reaction is coming from here. Okay, to this tiny part right on top of the roller. And then you may have some kind of a vertical force acting here, vertical force acting here. These two vertical forces will be balancing this vertical reaction. Okay, so these are the forces acting on this middle tiny part. So their counterparts, again, Newton's third law counterpart will be acting here. I'm just out of space, so that's why it is looking a bit cluttered. Okay, so if you got force P here, so how much will be this force? This force, it has to be P from Newton's first law. Okay, and then you got a net moment of PL acting, that is in the clockwise direction. So a counterclockwise moment here will be PL. Okay, and this sign is correct. This PL moment, because this will be counterclockwise, and there is a net clockwise moment of PL. So the two will balance. Now, since this force is P, this its Newton's third law reaction will be also P. Correct? Now, since this is zero length, also this moment will be PL. And I've got a support here. This support can have some reactions. You've got a moment of PL here. That means for moment balance, I have to get a force here. So how much will be the force here from moment balance of first part? How much vertical force will be here at this support? This moment you got, right? External moment PL is acting here. You agree with that, right?
Yes, sir.
So if I do the moment balance of first part, how do I get this moment to balance?
P.
There has to be a reaction here, right? So this length is 2L. The length of the first part is 2L. So this force has to be
P by 2, sir.
in this direction. In this direction, is the direction correct?
Also opposite directions.
opposite direction, right? So now you look at it, you got PL moment acting in the clockwise direction. And if I take a moment about this point, clockwise direction moment PL and anti-clockwise direction moment of PL, that is P by 2 multiplied by 2L, so PL. So PL and PL will cancel each other out. You got a moment balanced. Fine. So now this is force P by 2, that is vertical force. So therefore, it has to be, from Newton's first law, it has to be balanced by a vertical reaction here. That is P by 2. It's the equal and opposite part P by 2 here. So how much reaction will you have here? P and P by 2? 3P by 2. Okay. So drawing the reactions, you got P by 2 here. 3P by 2 here, you had P force here. Can you see the vertical forces are balanced? Sorry, my mistake here. Are the vertical forces balanced?
Yes, sir.
Yeah. Were you able to understand this entire thing, whatever we did just now? See, you did not have
Yes,
to
sir.
break it. If you had taken the overall equilibrium, you could have found these forces too. But I didn't want to basically skirt away from solving this locally also. So you can always split it into locally and again carry forward that forces. So that's what I was trying to emphasize on, that you can always break into smaller parts wherever you have confusion, how the forces are getting transferred, and still calculate the reactions. Okay. All right, so you got these external forces. From here, you can very easily calculate the bending moment diagram. You got for this part 2, you got 0 moment here, you got PL moment here, and this moment. Now, when you're drawing the bending moment diagram, you have to look at the bending moment. So for each part, if you see, for each small component, you have got a sagging moment, right? And as you move along in this direction, the moment keeps reducing linearly. That you can derive the expression for with respect to x. So you will see you've got PL here, and this is sagging moment. My sign convention is that sagging moment is negative. So I'll show it minus PL, but I draw it on the top side. So my sign convention is sagging moment is negative. And another part of the sign convention is I always draw bending moment on the tension side. Okay. So in a sagging moment case, which side is tension side?
Top
In a sagging.
sagging moment.
Oh, I'm
Bottom.
sorry. I was talking all. I don't know. This is not a sagging moment. Why didn't you stop me? This is a hogging moment. I was thinking hogging moment and I was calling it sagging moment. Really sorry. You guys should have stopped me there. This is a hogging moment and minus PL. In a sagging moment case, which side is the tension?
Bottom.
Bottom is the tension. So I will draw the bending moment at the bottom. In a case of a hogging moment, the top is in tension. So I'll draw the bending moment at the top. So that's why I draw the bending moment at the top, but I call it minus PL. Okay. Is that clear? Did I confuse you enough? You should have told me, guys. I was calling it sagging while it is hogging moment, right? Okay.
Yes, sir.
Yeah. I was thinking in my head that it is hogging moment. I was marking it negative. I was showing it upward. All that I was doing right. Just the words that I was uttering, I was calling it sagging. Okay. I hope I didn't confuse you too much. Then you got same PL moment on this side. Again, same hogging moment. So sorry, it is not matching. This will be also minus P. Okay. You can again derive the expression for a given x. You can try to derive the expression for given x. See the moment equilibrium, and then you will get the expressions. I'm sure you already know how to do this. Fine. So this is how you calculate the bending moment diagram, and then there are steps given in this method in these couple of slides where you can go through the steps. There will be double integration method, right? So I'm sure you are familiar with the double integration method. I don't want to go through step-by-step process. You can go through it, and then you can calculate the deflection at a given point, or you can calculate deflection everywhere. The advantage of the double integration method is over other methods is that at once you know deflection everywhere, because you derive an expression for deflection, right? So your expressions for deflection, this is y, right? That is given by this equation. Likewise, for part 2, the expression for deflection is given by this equation. So as soon as you find out the coefficients C1, C2, C3, C4, right, then you know the deflection everywhere. You can immediately plot it. But for any other method, if you use any of the energy method based methods or the moment area method or anything else, then you can calculate the deflection at one point at a time only, because wherever you apply the virtual load, only for that point you would know the deflection value. Okay, so this is one major advantage with this method, but it's a relatively longer procedure. It involves several steps. Okay, so I think I should stop here today. Any questions? I can take them. I have 5 minutes. Any questions?
So why you written as minus PL in that Benioff diagram? Just we can write PL now, or due to the hogging.
Yeah, because it's the, what am I saying here? Second moment is positive.
Due to the
I'm
hogging.
sorry. Yeah, so this is a hogging moment. That's why I'm calling it negative. In my sign convention, sagging moment is positive.
Okay.
My mistake. Sorry, I confused you today. Got this one. So my sign convention is here. This is positive. You can see this?
Yes, yes, sir.
The last one. So sagging moment is positive. I'm sorry, I was lost for 2 minutes. Okay. Please excuse me if I confused you a little bit on this one. You can refer to the lecture notes here. It is very clearly showing that sagging moment is positive. Sometimes it happens, you know, like you're thinking of a different word and you are saying a completely opposite of that. Yeah. So this is a positive moment for me, but I show it downward in a beam because that's the tension side. Okay. Any other questions? Okay, fine. All right then. I think I will give you one assignment based on this discussion due sometime next week, which will basically a kind of a recap of determinate systems, how to solve determinate systems, how to calculate deformations, etc. Okay, just to brush up your knowledge. All right, I think I should start doing more quizzes now. I think we have completed 1 week fully, right? Yeah, so it's high time we do one quizzes or assignment or something. Okay, fine. Thank you, folks.
Thank you, sir.
See you Monday.
Thank you, sir.
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 Bye-bye.